Welcome to the Dup Dive. Today, we're really unlocking the secrets of machine learning algorithms.
Uh-huh.
If you've ever felt maybe a bit overwhelmed by just the sheer volume of information out there, consider this your personal shortcut. A high-speed rail, maybe, to understanding the absolute core concepts, stuff you'd get from a really comprehensive online course.
Yeah, we're cutting through the noise, aren't we?
Exactly, getting straight to the insights that let you actually build things.
That's the plan. Our mission, really, for this deep dive is to demystify these powerful algorithms. We want to pull back the curtain on how they really work,
Right.
where they shine in the real world, and what it takes to actually put them into action. By the end of our chat, you should have a much clearer picture of what's under the hood.
It's giving you that foundation.
Exactly. A foundation to build some genuinely intelligent models. And we've sort of tailored this for a few groups, haven't we?
Yeah.
Aspiring data scientists, definitely. Software developers who are maybe curious about AI and ML.
Yeah, dipping their toes in.
Analysts who want to get more from their data. And, of course, students and researchers in computer science.
Makes sense.
Just a quick heads up, though. Having a bit of basic Python under your belt and some core math, linear algebra, a bit of calculus, probability, stats that'll definitely make the journey smoother.
Okay, good point. So let's unpack this right from the absolute beginning. What is machine learning, really? Because sometimes, honestly, it feels a bit like magic.
Yeah, it can seem that way. But at its core, machine learning is really about enabling computers to learn from data without being explicitly programmed for every single step.
So no rigid instructions.
Exactly. Instead of that, we feed them data, and they figure out the patterns, make predictions, adapt over time. It's essentially teaching a machine to learn from experience, kind of like how we learn, really. And we generally break this learning down into three main types. First up is supervised learning.
Okay.
Think of this like having a really patient teacher. You give the machine the input and the correct answers, right? And it learns the connection, the mapping between them.
Got it. Learning by example.
Precisely. Then there's unsupervised learning. This is more like learning without a teacher. The model gets data, but it's not labeled. It has to find hidden patterns or structures all by itself.
Discovering things on its own.
Exactly. And finally, reinforcement learning. This one's really learning by trial and error. You have an agent, it takes actions in some environment, gets feedback rewards or penalties, and over time, it learns the best strategy to get the most rewards.
Like training a dog, almost.
Sort of. And the general flow, the workflow, is usually pretty similar across the board. You collect data, clean it up that's crucial, pick an algorithm, train it, test it, see how well it did, and then hopefully deploy it.
And we see this stuff everywhere now, don't we?
Oh, absolutely. From like the movie recommendations you get on Netflix
Yep.
to spotting dodgy financial transactions or even helping doctors diagnose diseases. It's really widespread.
So practically speaking, if you wanted to get your hands dirty with this, you're setting up a Python environment first.
That's usually the starting point, yeah.
Yeah.
You want to bring in some key libraries. Scikit-learn is the big one. It's like your Swiss Army knife for ML.
Your tool docs.
Totally. Then you need pandas for handling your data, getting it into shape, and NumPy for all the heavy numerical lifting, the math stuff. Those three are pretty much your foundational toolkit.
Okay, essential tools. Got it. Now let's shift gears a bit. Let's talk about a really critical area, one that's just exploding right now, text analysis. Why is understanding language, natural language processing, NLP, why is that so incredibly important today?
Well, think about it. We are absolutely drowning in text data, aren't we?
Everywhere.
Every email, every customer review, social media post, news articles, even medical records.
Yeah.
It's just this massive ocean of unstructured information.
Right.
And the huge challenge, but also the enormous opportunity, is figuring out how to pull meaningful insights out of all that text chaos. You can't just, throw raw sentences at an algorithm and expect magic.
Doesn't work that way.
Nope. And that's why the very first, absolutely critical step is pre-processing text. This is where we clean it up, prepare it. It's maybe not the most glamorous part.
Yeah, probably not.
But honestly, it's fundamental. Your model's only as good as the data you feed it, and pre-processing makes that data digestible. There are several key steps involved here. First, case normalization.
Okay.
Simple idea. Imagine your text has apple, and maybe even APA. To a computer, those are three different things.
Right.
So we convert everything to a consistent case, usually lowercase. Why? It stops the algorithm from treating the same word as different entities, reduces duplication, improves accuracy. Simple, but important.
Makes sense. What's next?
Then we usually remove punctuation. Things like commas, periods, question marks, exclamation points.
Mm-hmm.
They often don't add much to the core meaning for
They're
analysis.
more about grammar.
Exactly. And they can just add noise, complicate things. So stripping them out simplifies the text. Next up, removing stop words. These are those super common words.
Like the, a is.
Precisely. The A is in, on, and. Words that appear constantly but rarely carry significant unique meaning for the analysis itself.
Of fluff.
Kind of, yeah. Getting rid of them does two things. It dramatically shrinks your dataset size, which is good, and it helps your model focus on the words that actually matter. Less noise, more signal.
Okay, that's clever.
Then what? After that, we do tokenization. Think of this like chopping the text up.
Into words.
Usually words,
Yeah.
Or sometimes smaller units like subwords.
Yeah.
You take that raw stream of text, the customer review or news article, and break it down into individual pieces, the tokens. These tokens are what the algorithms can actually count and process. Without tokenization, it's just one long, unmanageable string.
So breaking it into bite-sized pieces for the machine.
Exactly. And finally, there's stemming or lemmatization. Both of these aim to get words down to their root or base form.
What's the difference there?
Good question. Stemming is kind of the quick and dirty way. Basically just chops off prefixes and suffixes based on common roles. So running, ran, runs might all become run.
Okay.
But it can be a bit crude, like argument might become argue, which isn't a real word.
Ah, right.
Lemmatization, on the other hand, is smarter. It uses actual dictionaries and linguistic knowledge to find the true base form, the lemma, which is always a proper word. So running, ran, runs still become run, but better would correctly become good.
That sounds much better, more intelligent.
It is. It groups related words more accurately. This really helps improve your model's ability to understand the text and makes it more robust.
So let's say you're analyzing customer reviews, trying to figure out sentiment, positive or negative. All these pre-processing steps are totally essential, right? You're like refining the raw ore to get to the actual gold.
That's a perfect analogy. You're removing the irrelevant bits, the punctuation, the common words, standardizing the case so you can highlight the words that genuinely carry that sentiment, like love, hated, amazing, terrible.
It sounds like quite a bit of work before you even get to the cool machine learning model part.
It is, definitely. But honestly, this is where the magic often starts. Garbage in, garbage out, as they say. Clean data is everything.
Right. Okay, so pre-processing is done. Now, you mentioned something called Latent Dirichlet Allocation, or LDA. That sounds complicated. You said it's for unsupervised topic modeling. How does it find themes if there are no labels?
Yeah, LDA. It sounds complex, but the core idea is actually quite elegant, quite beautiful, really.
Okay.
It's unsupervised, like you said. It assumes that each document, say, a news article isn't just about one thing, but it's actually a mixture of several underlying hidden topics.
A mix, like different ingredients.
Exactly. Maybe an article is 60% about politics, 30% about economics, and 10% about international relations. And then it assumes each of those hidden topics is defined by a distribution of words.
Meaning
The politics topic is likely to use words like election, government, vote, bill frequently. The economics topic might use market, stock, inflation, trade.
Okay, I think I get the concept. Documents are mixtures of topics, topics are mixtures of words.
You nailed it. Conceptually, you can imagine how a document might be generated. First, decide the topic mix for the document. Then for each word you need to write, pick a topic from that mix, and then pick a word that's common within that topic.
Like, that's the generative idea.
Right. Now, the challenge for LDA, the inference part, is working backward. You give a whole bunch of documents, and it has to figure out what were those hidden topic mixes for each document and what words defined each of those hidden topics.
That does sound challenging.
It is computationally, but it's powerful.
Hmm.
The biggest pro is obvious. It discovers themes automatically without you telling it what to look for. It's unsupervised discovery.
That's cool.
It also helps reduce dimensionality, boiling down huge text collections into maybe 20 or 50 core topics. And often, the topics it finds are quite interpretable by humans. You look at the top words for a topic and you go, ah, okay, that looks like the sports topic.
So you could use it to automatically sort news articles into sections like technology, sports, politics.
Precisely. That's a classic use case.
Right.
But it does have its cons, its quirks.
Like what?
Well, first, it relies heavily on that pre-processing we just talked about.
That's right.
Second, and this is a big one, You usually have to tell it how many topics to find beforehand. You have to specify K.
How do you know how many topics there are? 5,
Eh,
50?
Exactly.
Hmm.
That's often the trickiest part. Choosing the right K can be more art than science sometimes. Trial and error. Also, sometimes the topics it finds aren't perfectly coherent. You might get a topic that mixes weird words together, and it uses a bag of words assumption.
Meaning it ignores word order.
Yes, it treats documents like just a collection of words losing the sequence. So man bites dog and dog bites man look the same to basic LDA.
Ah, okay. So for tasks where word order is critical, like maybe understanding subtle jokes or instructions, it might fall short.
It definitely could, yeah. For those nuanced tasks, you might need different techniques. But for just getting the gist, the main themes, in large amounts of the text, LDA is still remarkably effective.
Gotcha. Okay, moving on within text analysis. N-gram features from text. This sounds simpler. Unigrams, bigrams, trigrams, sequences of words.
Yeah, n-grams are much more straightforward. A unigram is just a single word. A bigram is a pair of consecutive words. A trigram is 3 consecutive words, and so on.
So how does using pairs or triplets help compared to just single words?
Context. That's the key benefit. Single words, unigrams, often lack context. Think about New and York. Separately, they're okay. But the bigram New York is a specific entity with a clear meaning.
Right.
Or think about classifying topics. The single words stock market crash are informative. But the trigram stock market crash is much more specific and powerful as a feature. It captures common phrases and gives the model a better sense of meaning by looking at words that frequently appear together.
So it adds a layer of contextual understanding?
Exactly. Helps capture phrases and slightly more complex ideas than just individual words allow.
Okay. Then there's feature hashing. You called it the hashing trick earlier. Sounds like a clever shortcut for, what, dimensionality reduction.
It is. It's a really neat technique, especially when you're dealing with absolutely massive amounts of text data. Like, think web scale.
Okay.
The problem with traditional methods is you often build a vocabulary, a list of all unique words or n-grams in your data. If you have billions of documents, that vocabulary can become enormous, right? Takes up huge amounts of memory.
I can imagine.
Feature hashing gets around that. It uses a hash function, a mathematical function, to directly map each feature, like a word or an n-gram, to an index in a fixed size vector. And crucially, it does this without ever building or storing that explicit vocabulary list.
Wow. Okay. So it just maps things on the fly.
Pretty much.
Yeah.
Its biggest advantage, its pro, is that it's incredibly memory efficient. You decide up front, I want a vector of size 1 million, and it maps everything into that fixed space. Great for streaming data or systems with memory constraints.
What's the catch? There's always a catch.
True. The main con is the possibility of hash collisions. Because you're mapping potentially billions of unique features into a smaller fixed space, it's possible that 2 different features might get mapped to the same index by the hash function.
Ah, so they become indistinguishable.
Exactly. The model can't tell them apart.
Yeah.
In practice, with well-chosen hash functions and large enough vector sizes, collisions might not be a huge problem, but it's a trade-off you make for the memory savings.
So best used for like high volume text classification where memory is tight.
That's a prime use case, yeah. When speed and memory are paramount.
Okay. And the last one in our text deep dive, word2vec. This one comes up a lot. Learning vector representations of words. You hear that phrase everywhere. And the famous analogy.
The king minus man plus woman equals queen 1.
That's the one. It sounds like magic. How does it actually achieve that understanding of relationships?
It is pretty amazing stuff. The core idea is to represent words not just as distinct symbols, but as dense numerical vectors. Think of them as coordinates in a high-dimensional space.
Like points on a map?
Kind of, yeah, but a map with hundreds of dimensions. And the key insight is that words that appear in similar contexts or have similar meanings are mapped to points that are close together in this vector space.
So cat and kitten would be neighbors.
Exactly, and cat-dog would be relatively close, but cat and, say, democracy would be very far apart.
How does it learn these locations?
It typically uses neural network models, like SkipRAM or CBOW, continuous bag of words. Essentially, these models are trained on vast amounts of text, and they learn by trying to predict a word based on its neighbors, or predict the neighbors based on the word. By doing this over and over, they learn which words tend to co-occur, and that forces words with similar usage patterns into similar vector representations.
And that allows for those analogies.
Yes, because the relationships between words get encoded in the vector arithmetic. The vector difference between king and man captures something like royalty minus male. If you add that difference to the vector for woman, you land very close to the vector for queen. It's capturing semantic relationships mathematically.
That's genuinely cool. And the applications.
Oh, huge. You can use these word embeddings for tons of downstream tasks. Building recommender systems that understand product descriptions similarity. Powering much more nuanced sentiment analysis. Finding related concepts in research papers or legal documents. Machine translation. It really revolutionized NLP.
Okay. Fantastic overview of text analysis techniques. Let's broaden our scope now and move into multi-class classification. So this is where our output isn't just yes, no, but one of several categories, right?
Exactly. Binary classification is 2 classes, multi-class is 3 or more. Think classifying an image as cat, dog, or bird, or maybe sorting customer feedback into complaint, suggestion, or praise.
And when we're judging how well these models perform, we use metrics like accuracy, precision, recall, F1 score. And the confusion matrix becomes really useful here, doesn't it? To see where the mistakes are happening.
Absolutely. The confusion matrix is critical for multi-class because it shows you not just if it made a mistake, but what kind of mistake. Did it confuse cats with dogs or birds with cats? That helps you diagnose problems.
Makes sense. So what are some common algorithms for this?
Well, a good starting point is often multi-class logistic regressions, an extension of the binary version we'll talk about later.
Oh.
It often works using strategies like one Vaser's rest or OVR. That means it trains, say, one classifier to distinguish cats from everything else, another for dogs versus everything else, and so on. Then it combines their outputs.
Right.
Or it might use a multinomial approach that handles all classes simultaneously. It's still a linear model, though.
So pros and cons.
Pros. It's fast to train, relatively simple, and the coefficients can give you some interpretability. You can see which features push towards which class. Cons. Being linear, it assumes the boundaries between your classes are, well, linear. It can struggle if the relationships are really complex and twisty.
In an example use case.
Classifying customer support tickets into predefined categories like billing issue, technical problem, account query, general feedback. That's a classic multi-class problem where logistic regression often works well.
Okay. What about something more powerful?
Then you get into things like multi-class neural networks. These use those interconnected layers of nodes, kind of mimicking the brain. For multi-class, the output layer typically uses something called a softmax activation function. What that does is give you a probability for each possible class, and all those probabilities nicely sum up to 1.
So it tells you how confident it is for each category.
Exactly. Pros. Potentially very high accuracy. They excel at learning really complex nonlinear patterns in the data. Super versatile. Cons. They can be data hungry, need lots of examples. Training can take a long time, computationally expensive, lots of hyperparameters to tune, which can be tricky. And they can be prone to overfitting if you're not careful with regularization.
And the go-to example here is often image recognition, right?
Definitely. Classifying images into thousands of categories, like an ImageNet. That's a hallmark neural network task. Identifying handwritten digits, things like that.
Okay. What else is in the multi-class toolbox?
Another really strong contender is the multi-class decision forest, often random forests.
Ensemble methods again.
Yep. Instead of one complex model, you build lots of simpler models, in this case, decision trees, and combine their predictions. For classification, it's usually majority vote. Each tree gets a slightly different view of the data, or considers different features.
And the benefit of that?
High accuracy, often rivaling neural networks. They're much more robust to overfitting than single decision trees. They handle nonlinear relationships really well, and generally they train faster than deep neural networks.
Downsides.
The main one is interpretability. A single decision tree is easy to follow, a forest of hundreds of trees. Much harder to see exactly why it made a particular prediction. It becomes more of a black box.
Use case.
Predicting customer churn is a good one. You might classify customers into likely to churn, medium risk, low risk. Decision forests are great for that sort of predictive modeling on tabular data. And just briefly touching on those strategies like one visa all, OVR, and one visas one, OVO. These aren't algorithms themselves, but ways to adapt binary classifiers for multi-class tasks.
Right, you mentioned OVR with logistic regression.
Exactly. OVO trains one classifier per class against all others. OVO trains a classifier for every single pair of classes. So if you have 10 classes, OVO trains 45 binary classifiers.
Wow, that's a lot.
It can be. But OVO can sometimes handle imbalanced data sets better. The pros and cons really depend on the underlying binary classifier you're using with them, like an SVM or logistic regression.
Okay, good to know they exist. One more for multiclass.
Let's talk about the multiclass boosted decision tree. Another powerful ensemble, but different from random forests.
How so?
Boosting builds trees sequentially. Each new tree focuses specifically on correcting the mistakes made by the trees that came before it. It's an iterative refinement process. Think algorithms like gradient boosting machines, GBM, XGBoost, Light GBM, Cat Boost.
Those names come up all the time.
They do because they're incredibly effective. Pros: often state-of-the-art accuracy on tabular data. They handle complex interactions well. Training is usually quite fast and they scale well. Cons: they can be even more prone to overfitting than random forests if you don't carefully tune regularization parameters. And they can sometimes require more memory.
And a typical use case.
High-stakes prediction tasks, things like credit risk scoring, classifying applicants into different risk tiers. Fraud detection is another big one. Anywhere you need really high accuracy on structured data.
Excellent. Okay, let's switch gears entirely now. From classification buckets to predicting actual numbers. Let's talk regression.
Right. So classification predicts a category label. Regression predicts a continuous numerical value.
Like predicting the price of a house or temperature tomorrow or sales figures next quarter.
Exactly. And we measure how good these predictions are using different metrics.
Yeah.
Not accuracy, but things like mean absolute error, MAE, the average absolute difference between prediction and actual, mean squared error, MSE, root mean squared error, RMSE, which penalize larger errors more heavily, and R squared, which tells you how much of the variance in the outcome your model explains.
Got it. So where do we start with regression algorithms?
The absolute foundation is linear regression. It's often the first algorithm people learn.
There's a straight line fit.
Yep. It models the relationship between your input features and the continuous output by fitting a linear equation, basically. A straight line in simple cases or a hyperplane in higher dimensions.
Pros and cons.
Pros: super simple, very fast to train, highly interpretable. You get coefficients that tell you exactly how much a one-unit change in an input feature changes the output, assuming the linear relationship holds. Cons: its biggest weakness is that assumption of linearity. If the true relationship is curved, linear regression won't capture it well. It's also quite sensitive to outliers. Extreme values can really pull the line off course.
And the classic example.
Predicting house prices based on square footage. Or predicting someone's weight based on their height. Simple relationships where linearity might be a reasonable starting assumption.
Okay. What if we need something more sophisticated?
Well, one interesting angle is Bayesian linear regression. It takes a probabilistic approach.
How does that differ?
Instead of finding the single best value for each coefficient in your linear equation, Bayesian regression estimates a probability distribution for each coefficient.
So it gives you a range of possibilities.
Exactly. It tells you not just the most likely value, but also how uncertain it is about that value. This is incredibly useful, especially when you have limited data. You get built-in uncertainty quantification, PROS. Provides those uncertainty estimates, can incorporate prior knowledge or beliefs into the model, often works well with smaller data sets. Cons: can be computationally more intensive than standard linear regression.
Where would that uncertainty be crucial?
Think about predicting the effectiveness of a new drug based on early small clinical trials. A single-point estimate might be misleading. Knowing the range of likely effectiveness, the confidence we have in that prediction, is vital for decision-making.
Makes sense. What else provides more than just a single number?
Fast forest quantile regression. This is another cool one. Instead of just predicting the average or mean value,
Which is what standard regression usually does.
right, quantile regression aims to predict specific quantiles of the outcome distribution. For example, you could predict the median, the 50th percentile, the 10th percentile, and the 90th percentile.
So you get a sense of the range, like best case, worst case.
Precisely. It gives you a much richer picture of the possible outcomes and the uncertainty around the prediction. Fast forest just means it uses an efficient ensemble method, often based on decision trees, to do this. Pros: provides that detailed understanding of the prediction distribution, great for risk assessment, scenario planning. Cons: the output is more complex to interpret than just a single number. You get multiple predictions, one for each quantile.
And an example.
Predicting future sales figures. Knowing just the average expected sales is useful, but knowing the likely range, the pessimistic forecast, 10th percentile, and the optimistic one, 90th percentile, is invaluable for inventory planning, budgeting, etc.
Very useful. Okay, what about data that isn't quite normal numbers? Like counts.
Ah, good point. For count data, things that are non-negative integers, like the number of clicks, number of text incidents, number of calls, standard linear regression, isn't ideal because it can predict negative values or non-integers.
Right, you can't have negative clicks.
Exactly. So for this, we often use Poisson regression. It's a type of generalized linear model specifically designed for count data. It assumes the counts follow a Poisson distribution.
Okay.
Pros. Properly models count data, ensures non-negative predictions, provides insights into factors influencing the count rate. Cons. It relies on the assumption that the mean and variance of the counts are equal, a property of the Poisson distribution, which isn't always true in real-world data. Sometimes the variance is much larger, which is called overdispersion, and Poisson might struggle then.
Use cases.
Predicting the number of customer service calls arriving per hour. Modeling the number of cars passing through an intersection. Predicting the number of faults found in a software module. Anything where you're counting events.
Got it. Back to more general regression, do we see forests and neural nets here too?
Absolutely.
Huh?
Decision forest regression works just like its classification counterpart, but instead of voting on a class, the trees in the forest each predict a continuous value, and these predictions are typically averaged together.
So similar pros and cons.
Pretty much. Pros: high accuracy, great at capturing nonlinear relationships, robust to outliers. Cons: can be memory intensive, less interpretable than linear models. Example: predicting energy consumption based on complex factors like weather, time of day, occupancy. And neural network regression also exists. Use a similar neural network architecture, but the output layer typically has just a single neuron with a linear activation function, allowing it to output any continuous value.
Same trade-offs as multi-class neural nets.
Largely, yes. Pros: highly accurate, fantastic for extremely complex nonlinear patterns. Cons: data hungry, long training times, computationally expensive, prone to overfitting. Example: complex financial modeling like predicting stock prices, though notoriously hard, or sophisticated weather forecasting models. And finally, boosted decision tree regression. Again, similar to the classification version, trees are built sequentially, each one trying to correct the residual errors of the previous ones, but aiming to predict a continuous target.
Top-tier performance again.
Often, yes. Pros: highly accurate, usually trains faster than neural nets for regression on tabular data, scalable. Cons: can still have a significant memory footprint, potentially prone to overfitting if not regularized. Example: predicting customer lifetime value, sophisticated sales forecasting.
Okay, that covers a lot of ground for regression. Let's loop back quickly to two-class classification. We touched on multi-class, but the binary case yes to true false, spam not spam is so common.
Absolutely fundamental. And the metrics are key here: accuracy, precision, recall, F1 score. And the ROC curve and its area under the curve, AUC, become particularly important for evaluating performance, especially
With imbalanced datasets.
Exactly. When one class is much rarer than the other, like fraud detection, simple accuracy can be misleading. ROC-AUC gives a better picture of the model's ability to distinguish between the classes regardless of the imbalance.
Right. So what are the workhorse algorithms for binary problems?
A classic is the two-class support vector machine, SVM.
We mentioned SVMs briefly with OV.
Right. For the binary case, the SVM tries to find the optimal hyperplane, the best boundary line or surface that separates the two classes with the maximum possible margin.
Maximum street width between the classes.
Good way to put it. And it uses the kernel trick to handle nonlinear data. It can project the data into a higher dimension where a linear separation does become possible. Pros: very effective in high-dimensional spaces, lots of features. Memory efficient because it only uses a subset of points, support vectors, to define the boundary. Cons: can be slow on very large data sets. Tuning the parameters like the kernel type and regularization can be tricky. Often works best when you have fewer than, say, 100 features.
Example.
Spam detection is a classic SVM application. Text classification in general. Image recognition sometimes.
Okay, what about something simpler?
The two-class average perceptron. This is a very simple, old-school linear classifier.
How does it work?
It iterates through the data, and every time it misclassifies a point, it updates its weight vector slightly to correct the mistake. The average part just means it averages the weight vectors over all the iterations, which tends to make the final prediction more stable. Pros: very, very fast to train, simple to implement. Cons: it's sensitive to the learning rate parameter, can be slow to converge if the data isn't easily separable, and being linear, it's not effective for nonlinear problems.
So for basic, quick and dirty linear classification.
Pretty much, yeah. Simple text categorization tasks, maybe.
Then we have the forests again, two-class decision forest.
Yep. Same idea as multiclass, but the ensemble of trees votes on just two outcomes. Pros: Good accuracy, fast training, robust to overfitting. Cons. Less interpretable than a single tree. Example. Predicting whether a user will click on an online ad. Click-through rate prediction.
And two-class logistic regression.
The binary version is arguably even more fundamental than the multiclass one. It's a linear model, but it uses the logistic or sigmoid function to squash the output into a probability between 0 and 1.
So it directly gives you the probability of belonging to the positive class.
Exactly, which is often very useful. Pros. Fast interpretable coefficients. You can see how features influence the log odds, outputs probabilities. Cons. Assumes linearity between features and the log odds of the outcome. Sensitive to outliers. Example. Predicting loan default. Yes, no. Predicting disease presence based on symptoms.
And boosted trees. Two-class boosted decision true.
Same boosting principle. Sequential trees correcting errors, but optimized for a binary outcome. Pros. Excellent accuracy, fast training, scalable. Cons. Potential for large memory footprint, needs careful regularization. Example. Medical diagnosis. Presence-absence of a condition. Fraud detection.
And finally, two-class neural network.
Again, neural network architecture, but typically with a single output neuron using a sigmoid activation to get that probability between 0 and 1. Pros. High accuracy, learns complex nonlinear boundaries. Cons. Needs data, takes time to train. Example. Image classification for binary tasks, like detecting whether an image contains a specific object. Example. Is there a car? Yes, no.
Great overview of the binary options. Now, let's shift to something a bit different. Anomaly detection. Finding the odd ones out, the needles in the haystack.
Right. Identifying rare items, events, or observations that are significantly different from the majority of the data. Super important for things like
Fraud detection, definitely. Network intrusions, maybe finding faulty equipment from sensor readings.
all great examples. It's about spotting the unusual. So how do we do it? One popular method is the one-class SVM.
How's that different from the two-class SVM?
Instead of finding a boundary between two classes, the one-class SVM tries to learn a boundary that tightly encloses the normal data points. Anything that falls outside this boundary is considered an anomaly.
So it learns what's normal and flags anything else.
Exactly. It doesn't need examples of anomalies to train, just examples of normal behavior. Pros. Works well in high dimensions, can be robust to some outliers within the training data. Cons. Can be very sensitive to hyperparameter tuning, getting the boundary tightness right. Computationally expensive for large datasets. Also generally better with fewer than 100 features. Example. Detecting fraudulent credit card transactions, where most transactions are normal.
What's another approach?
PCA-based anomaly detection. This leverages principal component analysis.
Which we know is for dimensionality reduction. How does that help find anomalies?
The idea is that PCA learns the main patterns, the principal components, that capture the most variance in your normal data. You can then project any data point onto these components and reconstruct it back into the original space.
Okay.
Normal data points should be reconstructed quite accurately, low reconstruction error. But anomalies, which don't fit the main patterns captured by the PCA components, will likely have a high reconstruction error when you try to rebuild them from that compressed representation.
Ah, because they don't conform to the normal patterns PCA learned.
Precisely. So you flag points with high reconstruction error as anomalies. Pros. Often fast to train, handles high-dimensional data well. Cons. Assumes anomalies are indeed different along those principal components. Performance can be sensitive to how many components you choose to keep. Example. Detecting faulty sensor readings in manufacturing a sudden spike or weird pattern would likely have a high reconstruction error.
Clever use of PCA.
Okay, let's move towards something we interact with daily. Recommender systems. Netflix, Amazon, Spotify. They're always suggesting things. How do they work?
Recommender systems are fascinating. Their goal is to predict a user's preference or rating for an item they haven't seen before. We evaluate them using metrics like precision at K, how many of the top K recommendations were relevant, recall at K, MAP, NDCG, which consider the ranking order.
And there are different types, right? Collaborative filtering, content-based. Yeah, those are the main paradigms. Collaborative filtering uses user behavior, like ratings or purchases.
Yeah.
Users who liked X also liked Y. Content-based uses item features. You like this sci-fi movie, here's another one with similar themes. Hybrid systems combine both.
Let's talk about a specific one, the wide and deep recommender. Sounds intriguing.
It's a really powerful hybrid approach, popularized by Google. It combines two parts, a wide part and a deep part.
Okay.
The wide part is typically a linear model, like logistic regression, that's good at memorization. It uses features like cross products of user and item IDs to learn direct common co-occurrence patterns. Like people who installed app A often install app B. It's good at remembering specific, frequent interactions.
And the deep part.
The deep part is a neural network, a feed-forward network, that's good at generalization. It learns dense vector representations, embeddings for users and items. These embeddings capture underlying latent features, allowing the model to discover new, less obvious relationships. It can recommend items that are similar in ways the user hasn't explicitly interacted with before.
So it combines remembering common pairs with discovering new similarities.
Exactly. That's the beauty of it. Pros. Combines memorization and generalization effectively, often leads to very high accuracy. Cons. Can be complex to design, implement, and tune properly. Example, recommending apps in an app store or products on a large e-commerce site.
What about another common one, SVD recommender?
SVD stands for Singular Value Decomposition. This is a classic collaborative filtering technique based on matrix factorization.
Matrix factorization.
Yeah, imagine you have a huge matrix where rows are users, columns are items, and the entries are ratings or interactions. This matrix is usually very sparse. Most users haven't rated most items.
Right.
SVD tries to decompose this large, sparse matrix into two smaller, dense matrices representing latent factors for users and items. Think of these latent factors as hidden characteristics, like for movies, maybe a factor represents comedy versus drama, or action-oriented.
So it finds hidden dimensions of preference.
Kind of, yeah. It learns these factors such that when you multiply the user factor matrix and item factor matrix back together, you approximate the original rating matrix, filling in the missing values. Pros. Very effective for collaborative filtering. Dimensionality reduction improves performance and efficiency. Cons. Suffers badly from the cold start problem. It needs interaction data to learn factors, so it struggles with new users or new items. Also can struggle with extremely sparse data.
Classic example.
Movie recommendations based on user ratings, like the original Netflix Prize Challenge. Music recommendations.
Works sense. Okay, nearly there. Let's touch on image classification. Making machines see. We treat pixels as features, right? But images are so complex.
Incredibly complex. Variability in lighting, scale, viewpoint, deformation, background clutter. It's a huge challenge. We need models that can learn hierarchical features from simple edges and textures up to complex object parts and shapes.
And for state-of-the-art results, we often hear about very deep neural networks. And you mentioned ResNet earlier.
Yes, ResNet, or residual network, with a massive breakthrough in deep learning for computer vision. The problem with making networks really, really deep was the vanishing gradient issue.
The learning signal getting lost.
Exactly. As the error signal propagated backward through many layers, it would get weaker and weaker, and the early layers wouldn't learn effectively. ResNet introduced a simple but brilliant idea: residual connections or skip connections.
Skip connection.
Yeah, they allow the input of a layer or block of layers to be added directly to the output further down. It creates a shortcut for the gradient signal to flow through. This seemingly small tweak allowed researchers to train networks that were much, much deeper than before, hundreds, even over 1,000 layers deep.
And that led to better performance.
Dramatically better. Pros: state-of-the-art accuracy on many image classification benchmarks, ability to learn incredibly complex features, widely adopted standard. Cons: training from scratch requires massive data sets like ImageNet and significant computational resources, GPUs. That's why transfer learning, using pre-trained ResNets, is so common.
And applications are everywhere, right?
Object recognition in photos, self-driving car perception, medical image analysis, detecting tumors, etc. It powers a huge amount of modern computer vision.
Okay, last major category for today. Clustering. Grouping similar things together without any predefined labels. Unsupervised again.
Exactly. The goal is to discover natural groupings or structures in the data based on similarity. Use cases include customer segmentation, finding groups of customers with similar behavior.
Or grouping similar documents together, maybe. Genetic analysis.
All good examples. Finding inherent clusters in unlabeled data. And the most famous clustering algorithm is probably K-means.
K-means, how does that work?
It's an iterative algorithm. You start by telling it how many clusters you want to find. That's the K.
Specifying K again, like with LDA.
Yep, that's a key parameter you need to choose. Then it typically initializes K centroids, cluster centers, randomly. After that, it repeats two steps. 1. Assignment. Assign each data point to the cluster whose centroid is nearest, usually based on Euclidean distance. 2. Update. Recalculate the position of each centroid to be the mean average of all the data points assigned to its cluster.
And it keeps doing that.
It repeats those two steps until the cluster assignments don't change much anymore, or the centroids stop moving significantly. The goal it's trying to achieve is minimizing the inertia, which is the sum of squared distances between each point and its assigned centroid, essentially making the clusters as tight as possible.
Pros and cons.
Pros. Simple to understand and implement, relatively fast, scales well to large data sets. Cons. You must specify K beforehand, which can be tricky. It's sensitive to the initial random placement of centroids. Different runs might give different results. It tends to assume clusters are spherical and roughly equal in size and density, so it can struggle with oddly shaped clusters or clusters with very different densities.
And a typical example.
Customer segmentation based on purchasing data, like frequency, amount spent. Grouping documents based on word frequencies, though LDA is often better for topics. Image segmentation sometimes. Anywhere, you need a fast, basic partitioning of data.
Wow. Okay, what an incredible journey we've just taken. Seriously. From the absolute basics of what machine learning even is, through all the nuances of cleaning text.
Yeah, the pre-processing.
Then diving into all these different algorithms for classification, multiclass, binary, then regression, spotting anomalies, building recommenders, even getting machines to see with image classification and group data with clustering. It's a lot.
It is a lot.
Yeah.
But understanding these core algorithms, not just knowing their names, but having a feel for how they work, why they work that way, and crucially, when one might be better than another, that really equips you. It helps you approach real-world data sets with much more confidence.
Yeah, moving beyond just importing a library and hitting .fit.
Exactly. It's about thinking through the whole process, building complete, effective machine learning pipelines.
And that, you, our listener, is precisely what this deep dive was all about. Trying to give you that shortcut, that distillation of a huge amount of complex information into hopefully some really useful, insightful nuggets, cutting through the noise.
Definitely. And maybe a final thought to leave you with.
Yeah.
Think about how even the seemingly simple algorithms we started with, like just cleaning text properly, or understanding basic linear regression, how fundamental they aren't just isolated tools. They are the absolute bedrock, the building block,
Foundation.
the foundation that then allows us to build upon them, to combine them, and ultimately tackle the really complex, maybe even futuristic problems. Whether that's predicting the next big economic trend, designing personalized medicine, or building truly intelligent systems that integrate into our lives in profound ways, it all starts with these fundamentals.